The disc is read using a beam of laser light which is focused onto the information layer through the transparent polycarbonate plastic as shown in figure 5.1. And there's your figure 5.1, which is a fairly complicated looking diagram. You can see the polycarbonate plastic here. You can see your information layer and the wee notches in the disc, and there's a lacquer over the top of that. And then this is how the laser reads it. It's focused through an objective lens, refracted at the air disc interface, and is reflected back again and refracted out again on its way out. Using the dimensions and angles given in figure 5.1, calculate the refractive index of the polycarbonate plastic. We'll just scan in a wee bit in the diagram there and see what information we have. We have 27 degrees, and this is your angle of incidence. So I is equal to 27 degrees. Just write that down here. Now, we don't have this angle of refraction, but we do have enough information to get it. We know that that distance there is 1.2 metres, and we know that this distance here is 0.35. So if I just draw this down here at the side, we'll try and calculate the angle that we need. This is the angle here that we need, and this is our R angle, and this is 0.35, and this is 1.2 millimetres. So therefore, if you calculate the angle, we find the tan of R, and that's equal to 0.35 over 1.2. R comes out to be 16.3 degrees. Excuse me. So N is equal to sine I over sine R, which is equal to the sine of 27 over the sine of 16.3. And that gives you an answer of 1.62. The refractive index. So it's the sine of 27 over the sine of 16.3, and that gives you 1.62, and that's your answer. Part C. The digital information is encoded onto the information layer using a series of pits. Figure 5.2 shows two rays from the laser beam shining onto the information layer at the near normal incidence. Half of the light is reflected from the surface of information, which is ray A, so you can see there, and half from the pit in the surface at ray B. The depth of the pit is exactly 1/4 of the wavelength of the laser light in the plastic. Explain the resultant waveform generated when the two waves are superposed after reflection. Now the depth of the pit is a 1/4 wavelength, but it also has a 1/4 wavelength to travel back again. So by the time it has got out of here again, that light at B there has travelled half a wavelength more. So B has travelled lambda over 2 more. Therefore, that means that A and B are half a time period out of phase or in antiphase. So whenever they superpose with each other, then destructive interference will occur. And your resultant waveform will have 0 or minimum amplitude. It depends on whether they're exactly the same amplitude to start off with. And then the reading head moves forward slightly so that both beams A and B are reflected from an area without pits. So they travel exactly the same distance before they superpose. That means that the waves A and B are in phase with each other. And therefore you're going to get constructive interference. And that means that you will have a maximum amplitude.